Now, I want to take a look at probability distribution functions for two variables. First of all, a function is a probability distribution function for two variables if it is a function of two variables, and it's always positive. And secondly, that the integral over the entire plane of this function is equal to 1. Okay, that's what makes it a probability distribution function. Now, x and y are two random variables, so you're measuring a couple of different things, and then you're figuring out what the probability of both those things happening at the same time is. Okay. Now, sometimes random variables are tied to each other, and sometimes they're not. For instance, if x and y were, let's say x was measuring the height of a person, pick a randomly chosen person, measure their height. Pick a randomly chosen person, measure their weight. So height is x and weight is y. And now both short people and tall people can be either skinny or fat, weigh a little or weigh a lot. However, it is probably the case that taller people tend to weigh more just because their bodies are bigger, right? So even though there is variation within each height, there would be some correlation between height and weight. These variables have a correlation between it. If there's no correlation, if knowing one doesn't tell you anything about the other, then we call these things independent. We say x and y are independent random variables. Essentially, if this probability function can be written as a product of the two individual single variable ones. So f of xy is equal to some g of x times some h of y, right? Where g is the probability function for x by itself, and h is the probability distribution function for y by itself. Okay. So independent variables. An example of that might be maybe x is measuring a person's height and y is measuring the average minute, the not average, but y is measuring the number of minutes late of a flight coming into London's Heathrow Airport. I mean, they're just completely unrelated to each other, and knowing, if I say, hey, I've picked a person at random and they weigh 102 pounds, what does that tell me about the arrival time of a particular flight coming into Heathrow Airport? I mean, it doesn't tell you anything. So they're unrelated to each other. We calculate probabilities now, just like we did before in the single variable case. You're not saying, you don't generally say, I want to know one particular value of x and one particular value of y. What's the probability of that happening? Well, it's going to be 0 because dA then would be 0. You generally give a region. You say, I want x between here and there. I want y in this range, right? So you're in the xy plane. You're describing a region of stuff. And you say, what's the probability of, when I randomly choose x and y, what's the probability of landing in that region? Okay. And the probability will be the double integral over this region D of the probability distribution function dA. Okay. So let's do an example of that. So the example I want to look at is number 32 out of the textbook. You have Xavier and Yolanda. They both have classes that end at noon, and they agree to meet every day after class. They arrive at a coffee shop independently. Okay. Xavier's arrival time is x, and Yolanda's arrival time is y, where x and y are measured in minutes after noon. Okay. The individual density functions are, so this is Xavier's probability density function for the time of arrival. Notice it's a decaying exponential. And it says here Xavier arrives sometimes after noon and is more likely to arrive promptly than late. And Yolanda arrives always gets there by 12:20, but is more likely to be later than earlier. Okay. Then we get the information that says after Yolanda arrives, she'll wait for up to half an hour for Xavier, but Xavier won't wait at all for her. Find the probability that they actually meet. Okay, well, here we go. So here's the information that was just given there. Here's the probability distribution. Yeah, try that again. The probability distribution function for Xavier's arrival time, and likewise for Yolanda's arrival time. Notice that this one does this, so he's more likely to be early and less likely to be late, but he may be really, really late. Small probability out here, but still possible. On the other hand, Yolanda will not likely arrive early, more and more likely as we get later, but never later than 10 minutes. Okay. Xavier won't wait, and Yolanda will wait for up to a half an hour, it says, so 30 minutes. So a couple things just to notice is that if I integrate this from minus infinity to infinity, of course it's 0 here, so really it's only integral from 0 to infinity. You can double check that this area is indeed 1. Likewise here, it's not too hard to check that this has height 1/5 and a base of 10, and you're talking about a triangle right there, so that does have area 1. Okay. Now, we need to figure out how they'll possibly meet, right? Well, Xavier won't wait, so Yolanda has to get there first. So we know that Yolanda's time has to be earlier than Xavier's time, right? So y is going to be less than x. On the other hand, x has to be earlier than 30 minutes after Yolanda gets there, right? So x has got to be less than y plus 30. So y is the time that Yolanda arrives. X is the time that Xavier arrives. And so this, I think, is the situation. Also, I know that both x and y are positive, right? So x is bigger than 0, y is bigger than 0. They get there after noon. There's no problem. There's no possibility of getting there before noon. So when I look at the xy plane, I'm seeing y has got to be less than x. So here's the line y equals x, right up through here. So for y to be less than that, you've got to be underneath that line. But I also have that x is less than y plus 30. Well, the line y plus 30 would hit the x-axis here at 30 and have slope 1. I know that also over here, I didn't write this down, but I know that y is less than or equal to 10. Right? I suppose this could be or equal to on those two, but y is never any bigger than 10. So there's a cutoff here at 10 that you don't ever get bigger than. So it looks to me like the region that we're talking about here, the possible times of arrival where they would actually see each other is in this range. So you've got something, you know, like a point here might be that Xavier arrives at well, let's say that Yolanda arrives 5 minutes after and Xavier arrives 10 minutes after, so Yolanda's sitting there waiting for him. Okay, only been waiting for 10 minutes and she'll wait for as much as 30. So this is the region where they'll actually meet. So I want to know what's the probability of that region. Okay. Now, they did tell me that their arrival times are independent. So my probability distribution function is going to be just the product of these two. Now, within this region here, I'm pretty sure that x is positive and y is between 0 and 10. So I'm not in the otherwise categories for either of those. I'm up here. So the probability distribution function is just the product of those two. So my probability distribution function looks like y over 50 times e to the negative x. right? And what I want to do is I want to integrate over that region D. Well, it looks to me like the easiest way to do that is going to be doing it horizontally. That is, for each value of y between 0 and 10, x runs from this line out to that line. Well, this is the line x equals y. That is, it's this condition here. I guess it's an or equal to on either of those, and the upper value for x is going to be when x is equal to y plus 30. Right? As long as Xavier arrives between Yolanda's time and 30 minutes after Yolanda's time, then they will meet. Okay, and so then it's a matter of evaluating this integral, which I calculate as, type it into my calculator and do the integral. I get 0.0199990 something. So essentially, the chance of them meeting is about a 2% chance. So much for meeting every day. It's like they hardly ever will meet. But, if we could get Xavier to stick around a little while, maybe it would happen. But that's the idea of a probability distribution function of two variables here, and the way we calculate probabilities based on that.